We're continuing on here with our differentiation skills. So far we can differentiate polynomials and products and quotients of polynomials, right? The product rule and the quotient rule. Next up we've got the chain rule, which is going to tell us how to differentiate compositions of functions. Alright, so what are compositions? I think this is worth reviewing before we get into the actual chain rule and start doing calculus. So compositions are the following. Given two functions f of x and g of x, we can take those two functions, and one way to form a new function is maybe you multiply them together, another maybe you add them together or divide them. But one of the fanciest ways of forming a new function from two given functions is you compose them together, right? So we form the composition function g of f of x. You could also do f of g of x, but for now we'll just focus on g of f of x, where what this says is instead of plugging in x into g, you plug x into f. And then you get an output, and then you plug that into g, right? So you start off with a number you start off with a number x, you plug that into your function f, and how do functions work? Well, you plug in a number, you get out a number, all right? So you plug in x, and you get out f of x. Then this number, whatever that number is, you plug that into g, and you get out a new number called g of f of x. I need another bracket here. Notation, by the way. I will typically use this notation because I like it the most. It shows exactly what's going on, but quite often people denote this the following. G of f of x, is that enough brackets? Yeah, g of f of x. Quite often people call this function g composed with f. Alright, so it's g with a little circle followed by f of x. Alright, so the composition g composed with f really is this brand new function that's quite often called g with a little circle f, g composed with f. But I will typically write this as g of f of x. So that takes these two functions, f and g, and it turns them into this single function, g composed with f. And unfortunately the notation doesn't really match the way you should think about this, right? Because f is applied first. X goes into f, that outputs something, and then that goes into g. Unfortunately, we read left or right, so this looks like g comes first, but it's really the f that's happening first. So I'll make this more concrete with an example. Alright, for example, here's our two functions. If f of x is, say, 2x squared plus 1, and g of x is e to the x, let's find g of f of x. So how should you read this? This is actually pretty simple to read, right? It says, okay, here's g of x is e to the x, except instead of plugging in x, everywhere I see x, I'm going to plug in f of x, right? So you can actually kind of think of this as g of 2x squared plus 1, if you want, right? It's the same thing, it's g of f of x, and that's what f of x is. So what does this mean? This means everywhere I see x, I plug in 2x squared plus 1. So this is going to be e to the 2x squared plus 1. Alright, so it's this composition of these two functions. Building them in the forward direction like this is actually pretty easy, as you've seen. But going backwards is a little bit trickier, right? When I give you an expression like this, you also need to be able to backwards engineer this and see that this is in fact a composition of functions, and it's built up as a composition in this way. All right, let's find f of g of x. Right, what does that mean? That means everywhere I see x in f, I'm going to plug in g of x, so that's f of e to the x. So everywhere I see x, I plug in e to the x. This will be 2 times e to the x squared plus 1. Or, remembering our exponent rules, this is 2 times e to the 2x plus 1. Alright, so just based on these two simple functions we have, by composition we built up these sort of brand new functions that are much more exotic. So this is an important skill. We'll keep going. We'll do another example. F of x is, say, 4x plus 1, And g of x is the square root of x plus 5. Let's find say g of f of 2. So one thing you could do is you could build g of f of x in general and then plug in x equals 2 and see what you get. But how about I just think of these as numbers? What is f of 2? F of 2 is, plug in 2 into this expression, 4 times 2 plus 1, that's 9, right? So g of f of 2 is going to be g, we just found f of 2 is actually 9, right? So it's actually g of 9. So now we're plugging in 9 to this expression. That's the square root of 9 plus 5. Square root of 9 is 3, plus 5 is 8. And that's the answer. Right, so this is how these compositions work, right? This means 2, I first plug that into f, and I get out a number. So I plugged in 2 into f, and I got out 9. And then I take 9, and I plug that into g, and I get out a number. And that number is 8. Alright, last example, we'll do quite a few because it's really important to understand compositions of functions. So write h of x equals 3x plus 1 cubed as a composition of two functions. Alright, so this is what I was saying in the first example. It's very easy to take two functions and compose them together, but if I give you a single function and I say, think of this as a composition, how do you sort of break it back apart into two different pieces that are composed together? And doing this comes, I think, with just experience. The more you do it, the easier it is to see. So I'll tell you how this one works. And the way you should think of this is I've taken the function 3x plus 1 and I've plugged it into something that cubes everything, right? So I've taken 3x plus 1 and I'm cubing the whole thing. So how do I build this as a composition of functions? Well, I want the function 3x plus 1. And I want the function 3x plus 1. And then I want to plug that into something that just cubes everything. Right? So what cubes everything? Well, how about just a cubic function? X cubed. Right? Then what's h? Then h of x is actually, so the last thing I do is cube. I think this is the outside function, right? The last thing I do on the outside is I cube. So g should go on the outside. And on the inside, I've got g of, everywhere I see x here, I've plugged in 3x plus 1. So this would be g of f of x. And if you compute g of f of x, well, that's g of 3x plus 1. So that means I plug 3x plus 1 into x, which gives me 3x plus 1 cubed. So it's important to be able to backwards engineer and think of these compositions, or think of a single function, recognize when it's a composition of other functions. But with that, we can finally start differentiating, I think. So, we have the chain rule. And here's the chain rule. Chain rule tells us how to differentiate compositions of functions. So I've got f of g of x. I've changed up the order here. Before we were doing g of f of x always, but I've just changed the naming scheme. So I've got f on the outside and g on the inside. And how do you differentiate f of g of x? Well, what you do is you differentiate the outside, so you take the derivative of f and you compose that with g. Right, so the outside stays the same, but the inside, or sorry, the outside gets differentiated, but the inside stays the same. And then you multiply this by the derivative of the inside function g. Okay, so this is derivative of f, which I like to think of as the outside function, composed with G or evaluated at G. Evaluated at G, which is the inside function. But that's only the first half of the chain rule, so the first half is you differentiate the outside function. The second half is you multiply by the derivative of the inside, derivative of G. So the inside function. And this is the famous chain rule. By the way, you'll notice everything here is written in terms of f prime, g prime, and so on. So this is sort of the Newtonian notation of the product rule, or the chain rule rather. It actually looks a little bit prettier if you use Leibniz notation, alternate form. So I'll just say this. I'll say if y is f of some variable u, not a good looking u. Right, so if y is some function of u, and u is in turn some function of x, so u is g of x, then dy dx, the derivative of y with respect to x, would actually be kind of hard to find at this point, right? Because you're given y as a function of u. So differentiating y with respect to u would be easy, but how do you differentiate with respect to x? Well, what the chain rule is really saying is it says take the derivative of y with respect to u first, and then multiply by the derivative of u with respect to x, du dx. And the reason why this is such a successful, such a nice form, and why Leibniz notation is so successful, is because of formulas like this. dy dx is dy du times du dx, and you can really sort of think of these as canceling. And if the du's cancel with each other, then of course it's just dy dx is equal to dy over dx. Full disclosure though, I'm not going to use this form very often or think about it much for now. When we get to a topic in the future, quite a few weeks down the road, we'll come back to this. But this is how I usually think of using the chain rule, right? Derivative of the outside function, evaluate the inside, times the derivative of the inside. And I have a little bit more good news for you, which is this is the chain rule in its full generality, right? It applies to all sorts of exotic functions for f and g, but in this class we don't really work with that many functions, right? We work with power functions, these polynomial things like x to the n. We work with exponential functions and logarithmic functions. And that means we don't need the chain rule in its full generality. I can sort of just tell you special cases for the chain rule for the types of functions we'll be working with. So this is special case number 1. Here's the chain rule applied to the types of functions we'll be working with for now. The derivative of, we know how to work with x to the n, right? How about this? The derivative of g of x to the n. Right, so instead of x cubed or something, maybe you've got like x squared plus 1, all cubed. And the chain rule in this case says that the derivative of a function of this form is going to, it actually works a lot like x to the n. The n comes out front, right? The n comes out front times the inside function, g of x, to the n minus 1. Right, so it's just like differentiating x to the n, where the n comes out front, the inside stays the same. Instead of having x here, I've now got g of x, and the power reduces by 1. But that's only the first half of the chain rule. Right? Remember the chain rule says it's the derivative of the outside function, evaluate the inside, and the outside here is actually this thing that raises everything to the n. So we've differentiated this nth power function, and the inside stayed the same, times, second half of the chain rule, what did it say? Times the derivative of the inside function. So times the derivative of the inside thing is times g prime of x. And this one is really worth committing to memory because it's the one special case of the chain rule we'll be using all the time. I'll give you a few more down the road, but for our lecture today, this is the formula we'll be using. All right, so for example, let's say f of x is 2x squared plus 3 to the power of 5. One way you could differentiate this is you could expand this whole thing out into a polynomial and not have to use any special rules. But expanding out a fifth power would take you quite a while, lots of algebra, wouldn't recommend it. Right? Another way of doing this is recognizing that this is of this form. This is a composition where my inside function is 2x squared plus 3, and then I've raised that whole thing to the power 5. Right? So we're going to use this special case of the chain rule that says first differentiate the outside function, this thing that raises everything to the 5. So the 5 comes out front, 5. The inside is going to stay the same, so I'll write in a second, but then our power decreases by 1 to the power 4. Right, so what's on the inside? Well, the inside is the original function. Right, the inside doesn't change. So this is 2x squared plus 3. Right, it's just like differentiating x to the power 5, except instead of having x, I have my inside function. The only catch is now I have to remember the second half of the chain rule. Now I multiply by the derivative of the inside stuff. What's the derivative of 2x squared plus 3? Well, it should be 2 times 2 is 4, x to the 1. So just times 4x. And last but not least, that's the calculus, but I probably should simplify this a bit or make it a little bit prettier. 5 times 4 is 20. X, you usually write that up front, times 2x squared plus 3 to the 4. So before now, this would be a very hard function to differentiate. Possible for us, but it would require lots of algebra. Now using the chain rule, I can treat it as a composition, right, as it actually is. This function is plugged into an x to the 5th function. And as long as I know this special case, this rule for differentiating functions raised to the power, then using this rule, it was actually a one-line process to get this derivative. So we'll do quite a few more. How about f of x is square root of x cubed plus x? Well, this is a composition, right? I've taken x cubed plus x, and I've plugged it into a square root function, right? What's the one catch, though? Remember, we don't work with radicals when we differentiate. We always convert them to powers. So that's a 1/2 power. And now it looks a whole lot like the last example we did, right? It's a function raised to a power. To the x cubed plus x is our inside function, raised to the power of 1/2. So the 1/2 power is our outside function. So our derivative is what? The 1/2 comes out front. The inside stays exactly the same. And we lower the power by 1. So 1/2 minus 1 is minus 1/2. But we're not done. Remember, that's only the first half of the chain rule. This is the common part that people sort of forget or mess up on. Is now, because I have a composition, because my inside isn't just x, I have to multiply by the derivative of the inside. So we'll differentiate the inside. Derivative of the inside is 3x squared plus the derivative of x, which is 1. And that's it. Maybe if you want to clean this up, make it look a little bit nicer. 3x squared plus 1 up top. Everything down below, we've got a 2 down here from the 1/2. And this negative 1/2 puts everything down on the bottom. And I'll go back to a square root because we started with 1. So over square root of x cubed plus x. And again, before now, this was really, this would be a complicated derivative. None of our rules would have worked on it, I don't think. Perhaps you could have done this with the limit definition, but it would have taken you a little while. But just using the chain rule, it was a one-line process. And now we're going to ramp up the difficulty a little bit, right? Hopefully you're convinced that now we can't do, before we could just handle x to the n, right? Now we can handle any function raised to the power n. So let's ramp this up a little bit. Here's a new function, x times 3x minus 2 to the fourth. And this is, if you look at the form of this is first and foremost, this is actually a product of two functions, right? If I think of this as x is my one function, times 3x minus 2 to the fourth is my other function. So it's one function times another. How do you differentiate products? Well, you use the product rule, right? So the product rule says it should be the first function times the derivative of the second plus the derivative of the first function times the second function. Right, there's the product rule in action. It's the first function times the derivative of the second plus the derivative of the first times the second function. So I haven't differentiated anything yet, I've just written down the form of the product rule. And now we'll actually differentiate, so we've got x times the derivative of 3x minus 2 to the fourth. Well, this is a function raised to the power of n, power fourth in this case, so we use the special case of the chain rule, which says 4 comes out front, the inside stays the same, and the power lowers by 1, so 3, times the second half times the derivative of the inside. What's the derivative of 3x minus 2? Just 3. And so we've differentiated this piece. What about the second half? Well, this is the one that's actually really easy. Derivative of x is just 1, right? So just plus 1 times 3x minus 2 to the fourth. And what do we want to do from here? I'm actually going to factor. Notice we have a 3x minus 2 cubed common to both of these pieces. So how about we pull that out? 3x minus 2 cubed, I'm going to factor that out from both of them. That will leave us with 4 times 3 times x is 12x from the first expression. And from the second expression, if I pulled out 3 of these 3x minus 2's, I have 1 left. So plus 3x minus 2 just to the power of 1. And clearly I can clean this up just a little bit more. I'll do it all right here though. If you want to combine these together, 12x plus 3x is 15x minus 2. Alright, so we just have a few more examples to do. 2 to be precise. So here's our function, f of x is 8x minus 1 to the power 7 over x plus 2. I think I will skip any heavy algebra that comes up here. We'll strictly differentiate this. And how do I differentiate it? Well, you look at the form, and what's the form? First and foremost, it's a quotient, right? So how do I differentiate quotients? Quotient rule. So we'll jump straight into this. Quotient rule says this should be low d high minus high d low, so the bottom, x plus 2. Remember, this bottom multiplies everything on the top, so I'm being very careful here to use brackets. It's really common to forget brackets or something, so this has to distribute. X plus 2 times the derivative of the top. I'm going to do this all in one go, right? So what's the derivative of the top? Well, we want to differentiate this expression. What is it? It's a function raised to the power n, so we use the special case of the chain rule. How do we differentiate the top? So the 7 comes out front, inside stays the same, then we lower the power by 1, and then we have to remember the second half, which says times the derivative of the inside. Derivative of 8x minus 1 is 8. Great, so we've got the bottom times the derivative of the top, now minus the top, 8x minus 7 to the 7th, times the derivative of the bottom. What's the derivative of x plus 1? Just 1. All all over, or sorry, derivative x plus 2, still 1 though, all over the bottom squared, x plus 2 squared. And I said I wasn't going to simplify, but I can't help myself. Let's simplify this as much as we can. 8x minus 1 to the 6th, that's common to both of these expressions. So I'm going to pull that whole thing out. We've got 8x minus 1 to the 6th. Then what are we left with? We're left with 7 times 8 is 56 times x plus 2 minus 8x minus 7. Right, we pulled out 6 of those powers, so we still have one of them left, so minus 8x minus 7 all over x plus 2 squared. And I'm just about out of space, so we'll see if we can just squeeze in the final answer here. 8x minus 1 to the 6th times, what do we have? We've got 56x minus 8x, that's 48x, plus 112, 56 times 2, 112, minus 7. So 112 plus 7 is plus 119, all over the bottom square. So a fun little example where we first applied the quotient rule, because it's a quotient of functions, so the derivative should follow according to the quotient rule, right, the form of the quotient rule. But we notice that the quotient rule requires us to differentiate the top, right? And differentiating the top, well, this is now an example of the chain rule, right? It's a generalized function to the n, so to differentiate that piece, we use the chain rule. And being able to combine these skills together is important, right? The last example, we first did the product rule and then we used the chain rule. So being able to combine these differentiation skills together is really important because more fancy functions require combining them together. We'll finish with one more example. F of x is 2 over 3x plus 1 to the 4th. So if I pause the video now and I said, go ahead and try this one on your own, feel free to do that, right? Try and do it on your own. But if you did that, if you paused it and you came back, you'll probably have done it a different way than I'm going to proceed. Right? Why? Well, because you're probably still thinking about the last example where, okay, I have a quotient here, so to differentiate it, I'm going to use the quotient rule. Right? But I've said this a few times already, and that functions are sort of, you differentiate them based on the form they're given, but you don't have to always accept the form that they're given. Right? You can change the form if you want. So right now it's written as a quotient. If I was going to differentiate, I'd use the quotient rule. But here's a little trick. Anytime you have a constant up top, like I have right here, it's really beneficial to change the form. Right? So if I only have a constant up top, I'm actually going to write this as 2 times 3x plus 1 to the minus 4. Right? Same function, written in a different form. And this is a major time saver because now I don't have to use the quotient rule, right? If I had a complicated function up here, I would still have a product, but here I don't even have a product because the top is just a constant, right? And what's the derivative going to be? Well, it's going to be 2 times the derivative of this stuff. So I don't even need to use the product rule, and our derivative is what? Right? This is why this isn't a product. This tends to throw students off once they learn the product rule. They start thinking of everything as a product, but if I have just a constant times a function, I don't need to think of this as a separate function in its own right. Right? Remember, the derivative of a constant times a function, you just pull the constant outside. Right? This is c times the derivative of f. So yes, I suppose formally this is a product, but if one of your functions is just a constant, just think of this as the constant times the derivative of 3x plus 1 minus 4. So this will be 2 times the derivative of this expression. Minus 4 comes out front. Inside stays the same. Lower the power by 1, minus 5. Right? Minus 4 minus 1 is minus 5. Times the derivative of the inside. Derivative of 3x plus 1 times 3. So what do we have? We've got 2 times minus 4 is minus 8. Times 3 is minus 24. And because this was originally given as a quotient, I'm going to convert this back to a quotient over 3x plus 1 to the power of 5. Quite a bit faster than using the quotient rule, although I promise if you did just go ahead and say, well, this is a quotient, so I'm going to use the quotient rule, you would get the same derivative. As long as you remember that when you differentiate the top here, derivative of 2 is 0, right? It goes away. So there's our answer. So we'll stop here. Our next two sections are learning how to differentiate logarithms and exponential functions. So once we have the derivatives of those, then we can really start building up some interesting compositions of functions using not just polynomials, but polynomials and logs and exponents, and products and quotients and compositions of all sorts of different things. But combining these three rules together, these fundamental rules of the product rule, the quotient rule, and the chain rule, combining them all together, you can end up differentiating just about anything that anyone could ever give to you.